Hello, in this video we're going to look at the multivariate sine test, and I'm going to suggest a couple background videos, background video 1, background video 2, where I calculate the probability being in the first quadrant and the fourth quadrant for a standard bivariate normal distribution. We're sort of going to make reference to those, so anyway, so let's keep going here. So the assumptions are that our observations are IID, so we're looking at a vector, and it's from a single population, and the CDF can be written like this. The second assumption is that these are absolutely continuous. So the CDF F is absolutely continuous. The univariate marginal CDFs, F1 through FP, are absolutely continuous, and the bivariate marginal CDFs are absolutely continuous. And the third assumption is that these theta 1 through theta p are the marginal median. So they're the median for each component in our vector. So the hypothesis that we're going to look at, and this is without loss of generality, is that the median vector is 0 versus that it's not 0. And it's without loss of generality because if we say that theta is equal to some theta 0, then we could take our original data x, subtract off this theta naught, and then our new data called y has a median of 0. And so we can easily transform it into this case. Now our test statistic, before I jump into the test statistic, I want to remind us what we did in the univariate case. In the univariate case, we looked at S as our test statistic, which was the number of data points greater than 0. You know, how many if we're proposing the median 0, then about half our data should be greater than 0. And if we get much more than half or way fewer than half our data meeting this condition, then something is not right. And then we showed that this is equal to the sum of an indicator function, where it was 1 if it was greater than 0 and 0 otherwise. And the reason we did this, then the sum of IID random variables, the central limit theorem, could kick in, and then it's asymptotically normal. Okay, but remember, our goal is the multivariate test statistic, and this is the univariate test statistic. And one thing to remember, when you have a test statistic, if we add constants to it, it doesn't change it, okay? So the test statistic that we just did is equivalent to this one, where we multiply it by 2 and subtract in. Remember, the test statistic is we reject if this is, say, greater than k. But if we were to add into both sides, then we're rejecting if this is greater than some constant. Of course, then we can divide by 2 to both sides, then we're rejecting if this is greater than some constant, but that was our original test statistic, so adding constants doesn't change it, okay? But this is equivalent to this. So if we think about n is the number of data points greater than 0 plus the number of data points less than 0. So if we put that in here, then the number greater than 0, then we have minus that, and there's 2 of them, so we're left with this. And then the number of data points less than 0, you know, is the minus piece. So this is equivalent to that. And this can be shown, so the number of data points greater than 0 minus the number of points less than 0 is equal to this sum of the sine function, where the sine function is 1 if it's greater than 0, 0 if it's equal to 0, and minus 1 if it's less than 0. And actually there's a sine function in R, but there they call it SING, and it's this function here. So the univariate test statistic is equivalent to this, the sum of the sine functions. And the reason we do that is going to make the development of the multivariate test statistic a little bit easier. So this is centered, so the mean of this is 0. But let's look at that. So now the multivariate test statistic uses the univariate test statistic in each component. So each component of our vector will have a univariate sine test, which is this. So it's this. So our test statistic, S, it's a vector, and in each component is the univariate sign test for that component, so SI is the sum of the sine functions, which we showed was equivalent to the number greater than 0 minus the number less than 0. Well, now let's start looking at the mean and the variance of our test statistics so we can look at additional distributional properties. So let's look at or investigate the mean of our test statistic under the null hypothesis. And we're going to do this in components. So this is the mean. This is our test statistic. So we're going to look at the mean of, say, this, and then the mean of the sum, because when we look at the mean of S, it's actually the mean of each component. So we're going to develop it incrementally here. So the mean of the sine function, and that means, the mean means what value can assume plus the probability of assuming that value added for each case. So the sine function can either be 1, 0, or -1, and then the probabilities associated with each of those events happening, which is this. Well, this is 0, and the probability that we're greater than 0 under the null is 1/2, and this is -1/2. So the mean of a sine function is 0. So that means if we look at a component, the mean of SI is going to be the mean of the sum of those, which then you can take in the expectation, and that's 0. The sum is 0, 0. So that tells us that the mean of our test statistic S is 0. It's the 0 vector. Well, now let's look at the variance of our test statistic. Okay? And again, we're going to do it incrementally. So the variance of the sine function means take each value it can assume, square it, times the probability of assuming that value. Now I left out the 0 case because it's 0. And then this is 1, that's 1, and so this is 1/2 plus 1/2 is 1. So the variance of the sine function is 1. Now let's look at the covariance of the sine functions. And one thing to remember is our indexing. So I is a component and K is a person or an observation. So when we look at the covariance between these two, it's the same observation or same person, and we're looking at different components within our vector. So the covariance of these sine functions is expected value of the product minus the product of the means. And we just showed that these are 0, so they go away. And when we look at the expected value, remember it's what value can assume times the probability of assuming that value. So the sine function, each individual one is either 1, 0, or -1. And so the product of those are either 1, 0, or -1, but the probability of assuming those is a little bit different. So here, the first, it could be a 1, so 1 times, and then the probability of assuming a 1 is they're either both positive or they're both negative. So it's 1 times this. It could be 0, but 0 times anything is 0, so I'm not even going to do that case. Or it could be -1. So -1 times the probability of us being -1. It can only be -1 if one is positive and the other is negative, or negative and then positive. And so this is the expected value. It's these individual probabilities. Now, I slip in this extra case here because in BV1, background video 1 and BV2, we look at these probabilities under the bivariate normal case. Okay, so normally we would have to stop because we don't know what the underlying distribution is. But in the bivariate normal case, we can show that it's 2 divided by pi times the arc sine of whatever the correlation is between those components. And anyway, I like BV1 and BV2, so I'd recommend going to see it. So now, since we looked at we're kind of developing the variance of our test statistic S incrementally. So now let's look at the variance of of a component of our test statistic. So the variance of SI, which is, this is the sum of the sine function, so you can bring it in, and then the variance of the sine function is 1. The sum from 1 to n of 1 is n. 1 plus 1 plus 1, etc. So now let's look at the covariance between the SI and SJ, the two components of our test statistic, which then SI is this and SJ is this. And so then for this, you can bring the double sum out front, and we look at the covariance between these two here. But one thing to remember, our data points are IID. So if we're within one observation, so there's P components, then there is a covariance. But if we're between observations, we're assuming they're independent, so the covariance is 0. So remember, K and L are observations or people, in some cases. And when K and L are different, then this covariance is 0. So really, when we bring out the double sum, it only applies when K and L are equal. Then we get a covariance. So that's what I do here. There's only one, when K and L are equal, so let's just call it K. And so this is the covariance between these two. And so it is whatever it is. So we can assume normality and then get some result. And I don't know if you can tell, I did that and I whited it out because we probably shouldn't do that just yet. So this is it. The covariance is whatever the covariance is. And under bivariate normal, it simplifies quite a bit. So the variance of our test statistic S, which S is a vector, so the variance is actually a matrix. So this matrix is filled with whatever this is, okay, which is this. And then, of course, in the multivariate normal case, it simplifies. Well, what are the diagonal elements of this? So the covariance of SI and SI, which is the variance, we know is 1. So the diagonal elements of this are 1. Okay, so we're almost there. So now let's look at the asymptotic distribution of S under the null hypothesis. So by the law of large numbers, these are IID, and then we're adding them up and dividing by n. So we know that this converges to the expected value of the sine function, which is 0. So this converges to 0. And remember, actually, so this is the test. This is one component of our test statistics. So each component converges to 0. So that's going to tell us that S converges to the 0 vector. Now let's look, and I call this Vij. So it's an estimate of our variance covariance matrix. So the sum of the sine functions divided by n converges to the expected value of these sine. So remember, and so since each, the mean is 0, this product is actually the covariance. So the covariance between those two. Now, we did under bivariate normal assume it was this, but in general we can't. So we just call whatever that covariance is Vij. So what we just showed here is that this matrix, remember, so this matrix V hat converges to V, so whatever it is. So now by the multivariate central limit theorem, we know this. Remember, S is it's the sum of things. So if we divide by n, then the multivariate central limit theorem tells us this converges to a multivariate normal 0, and then whatever the variance covariance matrix is, which is V. All right, that's what we just showed. Now, here, this is a little tricky, and people kind of abuse the terminology here. So this is an asymptotic result. So we need n's over here, because as n goes to infinity, it converges in distribution to this. But what some people do, remember this is the zero vector, so we can get rid of it. And then that cancels with this, and we have s divided by the square root of n. Some people take the n to the other side, square root of n, and then bring it in and say that s converges to a multivariate normal this. But that's not the case. You need the n's on this side to show asymptotic results. But so the correct way to say it, in my opinion, is for a given n, s is approximately multivariate normal with this case. When of course, yet when you take the n to the other side. So now that we know the distribution, we can find the rejection region. So the rejection, we reject h naught when this value is greater than some chi-square distribution with p degrees of freedom. And here's another little note, is that I have a video in my quadratic forms playlist that shows that multivariate normal, a quadratic form and multivariate normal like this goes to a chi-square. But here I used the actual v in my video there. But here this is an estimate of v. But since this estimate is a consistent estimate of v, and that's what we showed here, that we can use Slutsky's theorem, and then asymptotically this still does achieve the chi-squared with p degrees of freedom. And p is the number of components in our test statistic. Well, anyway, that's all I have for today. Hope you enjoyed that. Please like the video if you did, and subscribe so you don't miss the next one. Thanks. Bye.